Alright folks, welcome, and we'll kick things off with an introduction to static mechanics by looking at particles in 2D space. But first things first, statics. Why do we do it? So the point is to basically allow us to figure out what's happening to objects based upon loads that are applied to them. So if we are designing a bridge and we want to be able to drive big trucks over the bridge, and we want to figure out, as the trucks drive over that bridge, what sort of forces are the truck going to cause to the bridge itself overall, what sort of reactions are going to occur at the various points where the bridge is connected to these pylons or the ends and so on and so forth. And then we can go on and delve into more detail to figure out what sort of forces those are going to cause in the components of the bridge, so that we can size them properly, so we can make sure that we make them out of a strong enough material and that they're big enough, and thus they're not going to break on us. Same thing when we're talking with the wing of our airplane, so we can basically figure out what sort of forces are going to be applied to the wing by the aerodynamics of the air passing through it. Same thing with some of the other stuff. Our wing, we need to be able to figure out what sort of forces are going to be applied to the wing in order to make sure the dang thing stays in the air. And then we can use that to, again, size the individual components of the wing to make sure that it doesn't fall off on us, that it doesn't buckle, that it doesn't break. This nice fellow here with the prosthetic arm. We need to be able to ensure that we can calculate what sort of forces need to go through the arm, what sort of loads that thing needs to be able to support in order to do the things that he wants to do. He needs to be able to do in order to continue living his life to the fullest extent possible. And then we can use that to determine what sort of materials we need to make that prosthesis out of, and how large they need to be, and so on and so forth. So when we're looking at these problems, the first step is to formulate the problem. So we need to basically define what it is we're going to do before we start doing it. So we start by stating what we were given, state our desired result, and then state any assumptions and approximations. That gives us a baseline that we can start to work from. Then we further develop what we have. So draw any of your needed diagrams. Make sure you include your coordinate system. Diagrams are going to be insanely helpful to allow you to figure out exactly what it is that's going on. So those need to be neat, they need to be properly labeled, dimensions need to be included on them in order to make sure that you're putting stuff in the right place, so on and so forth. You need to state your governing principles that are going to be applied. What sort of physical principles are you working with? In this course, we'll primarily be using just we'll be working with Newton's first law. We don't get much further than that. Other courses, might be getting into other principles, thermodynamics, so on and so forth. But once you basically stated what principles you're using, and so defining what sort of calculations you're doing, you do them. They do need to be sufficient. You need to make sure that your accuracy is justified by the data. So you need to, if say, for example, you have been told to calculate how many lemons you can safely carry in a bucket based upon, the weight of how much weight the string attached to the bucket can hold. If you only know the average weight of a lemon to, I don't know, a quarter of a pound or so, then coming up with a calculation that tells us that you can hold, 35.382 lemons safely in the bucket, you're giving us a bit more detail than is necessary or justified. So make sure you're not trying to state more accuracy than you actually have. Then one of my big bugbears, ensuring that you're using consistent units throughout your calculations. So this is one of my main pet peeves, is doing engineering calculations. You're not doing math for the hell of it. You're doing calculations in order to get a particular result, and those results have units associated with them. So you're trying to calculate a force. You're trying to calculate a required area, cross-sectional area. You're trying to calculate the maximum length of a span. You're trying to calculate a temperature rise. So you do this by doing various calculations, multiplying and adding stuff together, and all those little things, they need to have units associated with them. And the good thing about doing so is it lets you catch a lot of your mistakes. If you end up with a value for the final calculation that's in meters squared per second squared, but you're trying to figure out a velocity, you screwed up somewhere. Probably forgot to take a square root, or forgot to cancel something out. Somewhere along the ways you screwed up. So it lets you figure out where you went wrong there. As well, ensuring you're using consistency through your calculations lets you avoid a lot of the common mistakes when it comes to using unit systems that you might not be familiar with. Again, in this course and others, you will be required to work with both SI units and various legacy imperial systems. I'm sorry for that, but that's the way it is. A fair chunk of engineering, especially aerospace, still works on imperial units. So you need to get used to that to a degree. So, if you accidentally plugged in feet where you should have plugged in inches, that is going to cause some problems for you. So ensure you're not making those mistakes. Actually track the units as you're throughout your calculations. I've seen students in the past who basically faked it. They put their units down, they cross them all out, and then they put down the unit that they thought they were supposed to get. But if they'd actually done the cancellations, they would have realized, no, I missed something here. I missed squaring this thing, and they would have saved themselves some pain. So don't do that. And then ensuring that your answers are reasonable. So reasonable magnitude, reasonable proper direction, especially when it comes to terms of stuff like ropes, chains, pulleys, so on and so forth. You can't push a rope. Common sense comes into play. Common sense and just getting a good idea for what sort of values you should be expecting. So at the end of the day, a lot of this just comes with experience, with practicing problems, continuation, repetition, so on and so forth. And then you draw your conclusions. When you draw your conclusion should basically be stating what you found the desired result to be. And then you solved your engineering problem. So when we talk statics of particles, it's an equilibrium problem. We got something that isn't moving, that or shouldn't be moving, and we want to figure out what sort of forces are applied to that thing in order to ensure that it doesn't move. Or, if we want to figure out, say what's if we have a particular rope that was attached to something that's holding something up, and we want to know, all right, how strong does this rope need to be in order to hold that thing without breaking? So oftentimes, in order to do so, we basically need to take a few forces that are acting on something that we can represent as a particle and add them together. This gives us what we call the resultant of those original forces. So so basically when we're doing force analysis on a particle, we're assuming that the particle has zero size. So all the forces acting upon it converge on a single point in space. So for example, we've got this pulley system here. These ropes are attached at this point here. There might be a ring there, some sort of hook, I don't know. It doesn't really matter too much. And then that's attached to the weight. So we can represent that point right there as a particle. Or we got a skydiver here. Again, she can generally be represented as a particle when she is in free fall. So she's falling down. There is one force that is pulling her down, gravity. And then there's another force that is pushing her upwards, the air resistance, the drag that is preventing her from accelerating as fast as she would have otherwise. Eventually, she's going to reach a point, which is called terminal velocity, where the drag pushing her upwards is the same amount as the amount of gravity pulling her downwards. So at that point, that's a statics problem. She's not accelerating anymore. She's moving at constant velocity. So when we talk forces, we characterize them by magnitude, direction, so both line of action and sense. This force is not the same as this force because it's acting in a different sense. It's the exact opposite direction. And then a point of application. So there's a couple ways of adding together these forces. So they are vectors because they have that directionality, because they have that magnitude. Essentially, I find that people do have, to some degree, a bit of an intuition in how to add vectors together, because they've been doing it their entire life when they're navigating. Because displacement is a vector. So if I tell you that in order to get from point A to point B, you need to go 10 kilometers northeast, that's a vector. That is a displacement vector. We got a magnitude, 10, got a unit, kilometers, and we've got a directionality. Northeast is pointing us in a particular direction. Same thing works for forces. So when we're doing things graphically, basically we represent the force as having a direction by pointing in a particular direction, and we represent its magnitude by the length on the page of the force of the line that we're drawing. So the length of these lines should be proportional to the magnitude of the forces they're representing. So when we need to add these vectors together, triangle rule works. Basically, you take if you have two forces that are acting on a particular object, you basically take one of the forces and move them from the object and basically put them tip to tail. So we have P1 here. We move on the page the P2 so that its tail is at the tip of P1. And then this basically gives us this shape here. And then we draw a line from the tail of P1 to the tip of P2. And that gives us our resultant. So when we add P1 and P2 together, the result is R. And then we go back to our basic high school trigonometry. We got our triangle rule. Allows us to calculate the sizes of these lines based upon the sizes of the other lines and the angles in between. So obviously, if P1 and P2 were perpendicular to one another, if this beta here is 90 degrees, then this thing here cancels out, and then we're just left with Pythagoras' theorem. I'm just going to state, oftentimes you may hear mention of the parallelogram law. So basically, you draw a little parallelogram based upon the two vectors in question. It's the exact same thing as the triangle law, and I don't know why any textbooks bother mentioning both. So if we have these four vectors here that we want to be adding together, we can do a multi-step process. So we take this green one, this blue one, add them together by taking the blue one, dragging it over to the tip of the green one. This gives us this purple one here as a resultant. Next step, all right, we've got that purple one as a resultant. Let's add the orange one to it. So this gives us this pink one as the resultant. Final step, all right, we got the pink one, add to it the red one, that's the final remaining one. And then this gives us our black resultant vector as well. So we could do a multi-step process. We don't necessarily need to. We can do it in a single step as well. We call the polygon rule. By just taking tip to tail, tip to tail, tip to tail, tip to tail, and then that gives us a single resultant. Order doesn't matter. It does not matter what order you add these vectors in together, as long as you just add them all together. So this arrangement, starting with green, blue, orange, red, works the same as start with blue, go to green, red, orange, still gives us the same amount. Order does not matter when adding vectors together. Another thing we can do instead is break these forces up into their directional components. So you're going to want to be doing that, breaking them up into components which are parallel with your coordinate system's axes, and then add those together. So start with these, break them up into vertical and horizontal components. So vertical, horizontal, vertical, horizontal, vertical, horizontal. And then you take those vertical and horizontal components and add all those together. So here we had three vertical components that were negative, and one vertical component that happened to be positive. Three horizontal components that were positive, and one negative horizontal component. And then just those plus that gives us this as a result. Same idea here. And then we can take those two resultants, the combined resultants of the various components that we broke it up, and then add those two together, and then it gives us the same vector that we started off with in the first place. So why would we do that? Again, far easier to deal with mathematically. If we're doing doing this instead of, say, trying to do these calculations at each step, dealing with all the different angles, keeping that in your mind. That's just a giant pain in the butt. So we don't want to be doing that. So it's easier to deal with mathematically, not dealing with the angles of each individual resultant between the steps. And of course, far, far easier to deal with vectors in 3 dimensions. Again, what we saw with the triangle rule is difficult enough to deal with if we only had a single dimension, but once we start getting in and out or up and down into the mix, things get really complicated really quickly unless you just break stuff up into your components and deal with and then add it all together at the end. So in order to do those calculations we talked about, we use what we call a unit vector. So basically they are directionality only. They are something that the concept of north. North is a unit vector. It tells you a direction. It doesn't tell you how much. It doesn't tell you what type of unit you're working with. And when I say it's a unitless directionality, that's different. It does not have it's kilometers or meters per second or anything attached to it. There's nothing physically associated with a unit vector, just a directionality. But if I tell you north, you know what direction north is. But if you want to go somewhere, you can't just be told north. You need to be told how far north. So you take a unit vector and you multiply it by a scalar united quantity to give you the vector. So 10 kilometers north is a displacement vector. Whereas, if we're talking forces, say 5 newtons in the x direction, that would be a force vector. So when we break various forces up into the directional components, basically we represent that with unit vectors. So I is a unit vector that is parallel with the x-axis, J is parallel with the y-axis, and K is parallel with the z-axis, but this lecture is on 2D stuff, so we're not going to worry too much about that. So we can take this vector here that we're talking about, and we can break it up into the 2 components. We've got the fx component, we've got the fy component. So the vector itself is equal to a force with a particular with that magnitude times that vector plus a force with this magnitude times the j vector. Add those magnitudes times the vectors together, and you get your overall force. So we can, if we're given the force and the angle, then we can figure out what the size of the components are, or vice versa. If we're given the size of the individual components, then we can figure out the overall size of the vector itself. And we can also figure out what the angle is based upon the sizing of the vectors as well. So we do have unit vectors for, in general. Each individual force that we're talking about will also have its own unit vector. So basically, or each direction that a force could be acting upon will have an associated unit vector. So we use lambda here to represent that. So basically, the way we calculate that is just figure out what's the relative portions of that force's I, J, and K vectors. So when we're talking 2D, the way we do that is just taking the, if we measure the angle between the vector and the x-axis in the xy plane, then we just take the cosine of that, multiply it by I, and that gives us our I portion. We take the sine of that, multiply it by j, and that gives us the j portion of it. So if this particular force was acting in the x-axis, then the cosine of that angle there would be 1, and we would be entirely I, which is what is expected. The sine of that would be 0. So again, what's expected. Exact opposite for if it was acting in the y direction, the cosine of that angle would be 0, and the sine of that the sine of that would be 1, so it'd be acting entirely in the j. One thing, so based upon that, since as I'm sure you recall from trigonometry, for any particular angle, the square of the cosine of that angle plus the square of the sine of that angle is equal to 1. So basically, when we take those unit vectors and add them together, we take these components of the unit vectors and add them together, the resultant of that is going to have a magnitude of 1. So essentially that means that when we take this unit vector and multiply it by a force, the magnitude of that, the overall magnitude of that force stays the same. So why are we breaking the stuff up? Because it allows us to be easily calculate our equilibrium. We're back to Newton's first law. So for those of you who don't quite understand the original Latin, here we are. Every body stays at rest or stays moving uniformly unless it's compelled to change by a force impressed upon it. So as long as the total resultant of all the forces applied to a particle is 0, its velocity is constant. For most of the stuff that we're talking about, that will mean it's remaining at rest. This means that if it's only acted upon by 2 forces, that's pretty easy to figure out. They have to have the same magnitude, they have to have the same line of action, and they have to have an opposite sense. So they're acting on the same line, just in opposite directions. So back to our skydiver example, she's being pulled down by gravity. She's being pushed up by the drag. When she is at terminal velocity, those two values, the magnitudes of those two are exactly the same, which means that she's at equilibrium. When you have 3 or more forces, we have a situation where a closed polygon is the graphical solution. So basically, when you take all these forces, put them tip to tail, you get back to the same spot. And again, when we're back to our analogy about navigation, if I go 3 blocks north, 1 block east, 3 blocks south, 1 block west, I'm back at the same place I was before. Same idea here. So if I am pushed to the side by a certain amount, pushed to the other side by a certain amount, up, down by the same amount, as long as everything cancels out, then I'm actually just staying at equilibrium, which is really the case right now. I'm sitting here, I'm being pulled down by gravity, but my chair is pushing back up at me by an amount equal to the amount that I'm being pulled down by gravity. So one thing we do use is free body diagrams. So basically, free body diagrams are a technique that allows us to remove any extraneous information and focus upon the forces that are acting on an object. So as opposed to, say, what your textbook here calls a space diagram. So space diagram is a sketch showing physical conditions of the problem. We got a truck, we got a load, we got ropes, we got pulleys, and so on and so forth. Again, typically it'll be given with the problem statement. We take that and we construct a free body diagram, which basically shows only the forces acting upon the selected body. In this case, we're looking at this little hitch here, or hook, or whatever it is in the middle that's connecting the ropes from the pulleys to the load. You remove the rope from the diagram, but you replace the rope with a force showing the tension in the rope. Obviously, that's going to be acting in the same direction as the angle, as the physical angle at which the rope itself is at. Another example, stolen from Wikipedia, you got a block on a ramp. So that's a space diagram. A free body diagram with just a block is going to be showing the gravity pulling downwards on the block. You got a normal force acting from the ramp to the block, and you've got a force of friction. So we can use these tools to basically allow us to determine what sort of forces are going to be acting upon the particle in question, and then at what angles they're acting at, and then from there do our calculations to determine what sort of resultants come out when we add and subtract the forces together, and then solve for any unknown forces. And that's pretty much it for 2D particles. So we'll be doing some examples later.